Okay, we're going to go on with section 4.4, analysis model, particles in uniform circular motion. Okay, the figure shows a car moving in a circular path, circular motion. If the car is moving with constant speed, it is uniform circular motion. So the analysis model is a particle in uniform circular motion. Even though the object moves at a constant speed in a circular path, it still has an acceleration. Why does it have acceleration if it's moving at constant speed? Because it's changing direction. Remember, the velocity vector is speed in a particular direction. So it's traveling at a constant speed, but constantly changing direction. It is accelerating. Let's look at the equation. Acceleration is equal to dv dt, the change in velocity over time, and the velocity, even though the speed is constant, the velocity is changing because the direction is changing. So the acceleration depends on the change in velocity. The velocity is a vector quantity. So acceleration can occur in two ways: a change in the magnitude of the velocity, or a change in the direction of the velocity. In this case, we're not worried about the magnitude changing. We're just talking about the direction changing. The object is moving with constant speed in a circular path, but it is changing direction. The constant magnitude velocity vector is always tangent to the path of the object and perpendicular to the radius of the circular path. So the direction of the velocity vector is always changing. Acceleration vector in a uniform circular motion is always perpendicular to the path. It always points to the center of the circle. If this were not true, there would be a component of acceleration parallel to the path, and therefore the parallel velocity to the velocity vector would mean that it's speeding up. Since the particle is moving at a constant speed along the path, we know that there is no acceleration vector in that direction. For uniform circular motion, the acceleration vector can only have a component perpendicular to the path, toward the center of the circle. Okay, now let's look at a close-up of the vectors. Let's consider the diagram of position and velocity vectors. Figure B below, that's the black position vectors and the red velocity vectors. The particle follows a circular path, the dashed curve of radius r. The particle at point A at time ti has a velocity at that time v sub initial. At B, sometime later, t final, the velocity is equal to velocity final, vf. Assume vi and vf differ only in direction. Then their magnitudes are the same. That is, vi equals vf equals v, because of uniform circular motion. And we're talking about the magnitude vector, the magnitude of the velocities, not the direction. Now, figure C, the velocity vectors are redrawn tail to tail. Vector V connects tips of the vectors, so it's vector addition. If you look, V final is equal to VI plus delta V. VI plus delta V, that's a head to tail summation. You can see that. But if you study this, you will see that delta V is V final minus V initial, which that is delta V, V final minus V initial. Both figures identify triangles. In figure B, the angle theta between the two position vectors is the same as the angle between the two velocity vectors in the right figure. Velocity vector V is always perpendicular to the position vector R. The two triangles are similar. Recall, if two triangles are similar, they are similar if the angle between any two sides is the same for both triangles, and if the ratio of lengths of these sides is the same. We write the relationship between the lengths of the sides for the two triangles. That's so the magnitude of the velocity vector divided by v is equal to the magnitude of the position vector, the difference in the position vector divided by r. Those relationships are the same, where v equals vi equals vf and r equals ri equals rf. Now, if we solve for delta v, we'll see that delta v is v script v times delta r over r. And if we divide that by delta t, we get the average acceleration. The equation gives the magnitude of the average acceleration over time interval for the particle to move from A to B. Okay? It's just delta V over delta T. Well, delta V is V delta R over R, and so if you divide that by delta T, you get the average acceleration. Okay, let's move on. Imagine points A and B in the figure become extremely close together. As A and B approach each other, delta T approaches 0. As delta R approaches the distance traveled by the particle along the circular path, the ratio delta R delta T is the speed v. The average acceleration becomes instantaneous acceleration at point A. In the limit delta t equals 0 or approaches 0, the magnitude of the acceleration is v squared over r. Okay, it's called the centripetal acceleration. This centripetal means center seeking. The subscript on the acceleration symbol, the little c, a sub c, reminds us that acceleration is centripetal for uniform circular motion. All right, let's continue. Now let's describe the motion of a particle moving with constant speed in a circle of radius r in terms of the period t. Period t is defined as the time interval required for one complete revolution of the particle. Repeat that. The period is the time interval required for one complete revolution of the particle. In time interval t, the particle moves a distance of 2 pi r, where r is the radius and 2 pi r is the circumference of the particle's circular path. So because the speed equals the circumference of the circular path divided by the period, v equals the velocity equals 2 pi r. That's the distance traveled over the time it took to travel. We get the period. If we swap the period and the velocity, 2 pi r over v. The period is the circumference divided by the velocity, the magnitude of the velocity. The period of the particle in uniform circular motion equals the measure of the number of seconds for one revolution. The period equals the measure of number of seconds for one revolution. The inverse of the period is equal to the rotation rate, measured in revolutions per second. The inverse of the period is the rotation rate, which is measured in revolutions per second. One full revolution of the particle around a circle corresponds to an angle of 2 pi radians. So the product of 2 pi and rotation rate gives the angular speed omega of the particle. So omega is equal to 2 pi divided by the period. And this is measured in radians per second or just inverse seconds, s to the minus 1. Sometimes we drop the radians. You'll see that in later problems. Now, the relationship between angular speed and translational speed with which the particle travels in the circular path is shown below. So the omega is equal to 2 pi divided by the period. The period, so if the period is 2 pi r over v, if we take the inverse of that, we get v over 2 pi r. And so all we get is v over r. So the velocity is equal to r omega. Okay, I lost my place. The angular speed and translational speed for the circular path is this. For fixed angular speed, the translational speed becomes larger as radial position becomes larger. All that's saying that is, if something is spinning, let's say you have a disk, and if it's spinning at a constant angular velocity, the outer portion of it is traveling faster than the inner portion. As an example, they say if the merry-go-round rotates at a fixed angular speed, the rider at the position at the outer edge, at the large r, is traveling through space faster than the rider at the inner position of the smaller r. If you ever been to the ice capades, they line up a whole bunch of skaters going around in a circle. They first someone's spinning, and then skaters join to it, and kind of the joke is that the very last skater has to skate very fast to catch up to the rotating line. That's this effect. The larger the radius is, the faster it's moving. Okay, we can express the centripetal acceleration of particle in uniform motion in terms of angular speed. So the centripetal acceleration, which is r omega squared over r. So that just, since that equals r squared omega squared divided by r, you just end up with r omega squared. This is centripetal acceleration. Okay, let's do a quick quiz. A particle moves in a circular path of radius r with speed v. It then increases its speed to 2v while traveling along the same circular path. The centripetal acceleration of the particle has changed by what factor? 0.25, 0.5, 2, 4, or it's impossible to determine. Okay, and just let you think about it. Try to find the I'll go back and help you. Acceleration is equal to v squared r. See the little blue box? Centripetal acceleration is equal to v squared r. So let's look at this question again. The centripetal acceleration of the particle has changed by what factor if the velocity has changed from v to 2v? Well, if it's v squared over r, that becomes 4v squared over r. So D is the correct answer 4 times. Okay? Now, a particle in a circular path of radius r with velocity v, with speed v, it then increases its speed to v while traveling along the same circular path. By what factor has the period of the particle changed? So let's look, see where they show the period. Okay, let's look back at this. If you look at the blue square there, the period is equal to 2 pi r over v. Well, if you go from v to 2v, how does that change the, by what factor has the period of the particle changed? Is it a quarter, a half, 2 or 4, or impossible to determine? Well, of the period, let's go back to that blue square. T is equal to 2 pi r divided by v, and if all of a sudden v is now 2v, well, you've changed it by a half. Oops, there's the answer. B is the answer. It's changed, the period is changed by 1/2, by 0.5, 0.5. Okay, let's look at, now that we've done that quiz, let's look at analysis model, particle. We're still looking at analysis model, particle, and uniform circular motion. Imagine a moving particle that can be modeled as a moving object that can be modeled as a particle. If it moves in circular path of radius r at constant speed v, the magnitude of its centripetal acceleration is, oops, two clicks. Centripetal acceleration is v squared r. The period of the particle's motion is 2 pi r over v, and the angular speed omega is 2 pi over t, which is the period. So some examples of an object moving in uniform circular path would be a rock twirled in a circle in a string of constant length. You can think of twirling a rock around your head if it's tied to a string. A planet traveling around a perfectly circular orbit. We'll learn that most orbits are elliptical, but they're very close to being circles. A charged particle moving in a uniform magnetic field. We'll get that in the next semester. An electron in orbit around a nucleus in the Bohr model of the hydrogen atom. That's the old-fashioned model. Now it's a probability cloud. All right, let's look at the examples. What is the centripetal acceleration of the Earth as it moves in its orbit around the sun? Well, we can model this, conceptualize. We can model the Earth as a particle and approximate the Earth's orbit as circular. Again, it's actually slightly elliptical. The amount of elliptical, how much it is elliptical is called the eccentricity, but we'll get into that later. You categorize the problem. The conceptualized step allows us to categorize this problem as one of a particle in uniform circular motion. Let's analyze it. We do not know the orbital speed of the Earth to substitute into the equation for the centripetal acceleration, but we can use the relationship between period and velocity to recast our question. So the acceleration, the centripetal acceleration is equal to v squared over r, and since v is equal to 2 pi r over t, v squared is equal to 2 pi r t squared. So v squared over r is 2 pi r t squared over r. We end up with 4 pi squared r over t squared. You'll see that the r cancels with the r squared on top. Sorry about the dogs. There's nothing I can do. There's probably there's someone walking. That's why they're barking. They'll settle down a little bit. I apologize. I lost my place. Okay, we know the period of the Earth's orbit is 1 year, and the radius of the Earth's orbit around the sun is 1.496 times 10 to the 11th meters. Now that's not something I expect you to know off the top of the head, but you can get it from the cover data of your book. So we substitute the numerical values. We know that the period is 1 year. The Earth travels around the Earth in 1 year. And we got the radius from the inside book cover. So 4 pi squared times the radius divided by the period squared is 3.156 times 10 to the 7th seconds in a year. And if you multiply that out, we get 5.93 times 10 to the minus 3 meters per second squared. 5.93 times 10 to the minus 3 meters per second squared. That's a very, very low acceleration. Well, it is. The acceleration is much smaller than the free fall acceleration of the surface of the Earth. An important technique we learned here is replacing the speed v in the equation for centripetal acceleration in terms of the period t of the motion. In many problems, it is more likely that t is known rather than v, the velocity. Okay. What is the angular speed of the Earth in its orbit around the sun? Well, we can substitute numerical values into the equation for angular speed. And we get omega is equal to 2 pi over the period. And the period, we can translate that to seconds by 1 year equals to 3.156 times 10 to the 7th seconds. And we end up with 1.99 times 10 to the minus 7 inverse seconds. We see that the angular speed of the Earth is very small, which is to be expected because the Earth takes an entire year to go around the circular path once. Okay? Now this ends our discussion of particle and uniform circular motion. Next, we'll be tackling section 4.5, tangential and radial acceleration.